In this video, we'll review some basic concepts of probability. We'll talk about vocabulary, as well as the difference between classical and empirical probability. So first of all, we have three concepts that are important to understanding probability: probability experiments, outcomes, and sample spaces. A probability experiment is a process that leads to well-defined results called outcomes. So these are experiments that you would actually do, like flipping a coin, rolling a die, or drawing a card from a deck. The outcomes are the results of that experiment, and we consider a single outcome to be the result of a single trial. So trials would be just one stage of the experiment, so like flipping a coin once, if the entire experiment involved flipping it multiple times, rolling a single die, drawing one card from a deck. Then the outcomes, just think about what are the options that you could get when you do one of those trials. So heads or tails would be the results when flipping a coin. Rolling a die, you would have 1, 2, 3, 4, 5, or 6. And then think about all the outcomes possible for drawing a card from a deck. You would have all of the number cards, all of the face cards. Okay, for example, the ace of hearts or the 10 of diamonds. A sample space is the set of all possible outcomes of a probability experiment. So think back to when we talked about sets and we used braces and listed things out. Right, so think of a sample space as a set or a collection of all of these possible outcomes. All right, so here are some examples of experiments and sample spaces. If the experiment is tossing a coin, right, then the sample space would be the list of possible outcomes, head and tail. Then if the experiment is rolling a die, hey, we've got 1 through 6 as the possible options in the sample space. Answering a true-false question, then the sample space would be true or false. And if the experiment is tossing 2 coins, then the sample spaces become those pairs of options. You could get heads on each coin, tails on each coin, a head on the first one and a tail on the second, or a tail on the first and a head on the second. Okay, so that would be 4 different options in the sample space. An event is any subset of the sample space of a probability experiment. Okay, so we talk about the event of obtaining an odd number when a die is rolled. And we would say, what is the probability of that event? Or what is the probability of the event of choosing a black card or a heart from a deck? Now here's some notation, and here we'll talk about classical probability. So we are working under the assumption that every outcome in a sample space is equally likely. So this is more of the theoretical probability. This is not the type of probability where you actually flip a coin and see what the results are. Right? This is theoretical, meaning, if you theoretically were to toss a coin, then you would have a 50-50 chance of getting either heads or tails. So some notation and a way to calculate classical probability. Let E be the event in the sample space. We call S the sample space. Right? And then we use this notation N of E, and this stands for the number of outcomes in E. Right? So it's using function notation. You may remember seeing something like f of x if you've studied algebra, and this is similar to that, right? And it's not a multiplication here, but this is more of like a label. So we would read this N of E, and it represents the number of outcomes in E. N of S is the number of outcomes in the sample space. So we have basically like a part here, the number of ways of getting the event that we're interested in, and then we have a total, the number of options or outcomes in the sample space. Okay, those are all of the possible options that could occur. So then probability of an event, we represent that with P of E, and probability is N of E over N of S, or the number of outcomes in E divided by the number of outcomes in S. So let's look at an example, and I think this will become more clear with some specifics here. All right, a single die is rolled. Find the probability of getting each of these events. So all of these are going to be our options for what we'll consider to be E. Okay. Now to calculate the probability of each of those events, we need to know the number of outcomes in that event, or how many ways are there for that thing to happen. And we also need to know the number of options in the sample space, okay, the total number of possibilities of what could happen. So if we're looking at the experiment of rolling a single die, let's first of all figure out what the sample space is. Okay, so S in this case would be all of the possible outcomes when you roll a single die. And we've talked about this one previously. This is 1, 2, 3, 4, 5, and 6. Alright, so we're going to end up with probabilities that are fractions, and they're all going to be divisible by or divided by 6. Okay, since we're looking at the number of ways to get something out of 6 total options. So let's look at the probability of rolling a 2. Okay, so the probability of a 2, and sometimes we'll put the number here in parentheses. Okay, the probability of getting a 2. Well, how many ways are there to get a 2 when you roll a die? Well, just one. We only have 1 2 on that die. Okay, so there's one way to get a 2. And then how many options in the sample space? We said that there were 6. All right, so 1 out of 6 ways of rolling a 2. What about the probability of getting a number less than 5? So here we want the probability of rolling a 1, 2, 3, or 4. Okay, well, that pretty much lays it out for you. If you list it that way, we see that there are 4 ways to get a number less than 5, and we already know that there are 6 total. Okay. Now probabilities we usually give as fractions in lowest terms. Right, so I would write this as 2/3. You sometimes will also see decimals or percents, but in this case we would get a repeating decimal, so rather than round, I've decided to leave it as a fraction. Alright, how about the probability of getting an odd number when you roll a die? Alright, well that would be 1, 3, or 5, so 3 ways out of 6, so that probability would be 1/2. And then what's the probability of getting a number greater than 7? A number greater than 7. Okay, so like 8, 9, 10, etc. Alright, well there are no numbers greater than 7 on a die, so that would be 0 out of 6, and we would just write that as 0. Alright, so it is possible to have a probability of 0. Alright, and a second example. 2 coins are tossed. Find the probability of getting 2 heads, at least 1 head, and at most 1 head. So first of all, what is the sample space? And we've listed this one as well. When you're tossing 2 coins, the options were either head, head, tail, tail, head, tail, or tail, head. And we do count head, tail, and tail, head as 2 different options, since these are on different coins, and we don't know in this case if the 2 coins are identical, like maybe one is a penny and one is a quarter. Right, so in this case, maybe we are concerned with which coin is which. Okay, the probability of getting 2 heads. All right, well that would be head, head. There's only one way to do that out of 4 possible options. Okay, so probability of 1/4. The probability of getting at least 1 head. So at least would mean exactly 1 head or more than that. Right, so our possible options are head, head, or head, tail, or tail, head. So 3 out of 4 ways for that event to occur. And the probability of getting at most 1 head, so it could either be 1 or none. So that would be either heads, tails, tails, heads, or tails, tails. And again, this is also 3 out of 4. Okay, so probability of 3/4. Now some observations about probability. First of all, it's never negative. Right, so the smallest you can have would be 0 ways out of how many things in the sample space. Okay, and then probability is never greater than 1. So there are only so many ways for an event to occur, and in the sample space we've listed all of them. Okay, so like if we looked at the example with rolling a die, Right? There are only 6 possible outcomes. So if you say what is the probability of, like the maximum probability, it would be 6 out of those 6 ways to get a certain event. Right? And of course 6 out of 6 is 1. So 0 is the smallest probability you can have, and that means that an event cannot possibly occur, like rolling an 8 on a die. If you have a probability of 1, that means an event is certain to occur. So if I said what is the probability of rolling a single-digit number on a die, while all 6 of those options are single-digit numbers, we're certainly, definitely going to roll a single-digit number on the die. And then the sum of all of the probabilities of all the outcomes in the sample space will always be 1. So this doesn't mean the sum of all of the possible probabilities for every problem we can think of is 1. It just means of all the outcomes in the sample space. So for our die example, right, if we looked at the probability of each one individually, like what is the probability of getting a 1, probability of getting a 2, probability of getting a 3, etc., those are all going to be 1/6. Okay, and then of course you have 6 of those options, right, or 1/6 added to itself 6 times, and that's going to be 6/6, which is 1. All right, what is the probability that an event will not occur? So one option is to just add up all the ways in which that can happen, but we also have a second method, all right, that we could use. So suppose a single die is rolled. What is the probability that a 4 will not occur? Now we use another notation from set theory. It's this little complement symbol. It looks like an apostrophe, except it's a little bit straighter than that. All right, so you can read this. What is the probability of 4 not, or 4 prime, or the probability of not getting a 4? Okay, so the probability of not getting a 4 would be, all right, think about which things we could roll on the die, and that would be a 1, 2, 3, not 4, 5, or 6, and that probability would be 5 out of 6 of those ways. All right. Now notice here, this actually works out to be the same as taking 1 and subtracting the probability of getting a 4. Right? So 1 is the probability, the sum of all of those probabilities, of all the numbers you could roll. Then when you subtract the option that you don't want, the probability of getting 4, or 1 out of 6, you're left with the probability of not getting 4. Right? So this is kind of a shortcut method to finding the probability of not getting something. Okay? For any event E, if E complement means the event that E does not occur, then we can find that probability by taking 1 and subtracting the probability that the event does occur. So sometimes this is nice if you had a lot of things to add up. Let's say that the probability was, or like, let's say the sample space was 1 through 100. Okay, and let's say that you wanted to know what is the probability of not getting a 99. Right? Well, in some situations, if this wasn't easy to count, maybe you'd have to add up, all these numbers except for 99, okay, all the way up through 98, and then 100, and you'd have to count all of those up, okay, divided by 100 options, etc. All right, or the shortcut is to just subtract 1 minus the one option that we don't want. So let's try it out in a problem. Of the next 32 trials on the docket in a county court, 5 are homicides, 12 are drug offenses, 6 are assaults, and 9 are property crimes. If jurors are assigned to trials randomly, what is the probability that a given juror won't get a homicide case? Okay, so we want to know the probability of not getting a homicide. I'll call that H. Okay, so let's use the formula. It would be 1 minus the probability of getting a homicide case. All right, well, what is the probability of getting a homicide case? Okay, so we have 32 trials altogether, and out of those 5 are homicides, so the probability of homicide would be 5 out of 32. All right, and then you can use a calculator to calculate this, or get a least common denominator. All right, so this is 32 over 32 minus 5 over 32, and that would be 27 out of 32. Right. Now think about how we'd have to do this if we use the addition method. Right? I'd have to add up all of the things that are not homicides. So I'd have to add, okay, the 12 drug offenses, that probability, 12 out of 32. Okay, the 6 assaults, and also the 9 property crimes. Okay, so we have 1 minus one thing, or the addition of 3 different things. And picture if we had many different crimes here, more than just those 3, maybe we'd have a lot of different things to add up. All right, let's talk about empirical probability. So we've already talked about classical, the more theoretical type in which all the events are equally likely. Empirical probability is the kind that is based on what actually happens in real life through some sort of a trial or an experiment. All right, so this is based on observed frequencies, not necessarily what you're expecting to find theoretically, and each event is not necessarily likely to occur. So if the trial or the experiment was flipping a coin, right, then maybe in real life it's not equally likely that you would get a heads as opposed to a tail. So maybe in a real experiment, maybe you get heads 4 times and you get tails only once. So we have a slightly different formula for probability. It's the observed frequency of a specific event, which we call F for frequency, divided by the total number of trials rather than options in a theoretical sample space. Okay, so for the example that I just did, what is the probability of getting a tails? All right, well, the observed frequency, or how many times we see tails, is 1. And out of the total number of trials, okay, I've recorded 5 here, so this would be 1 out of 5. Here's another example. Here's another coin toss, and you can see from this one the empirical probability of getting heads is 6 out of 10. There are 6 heads showing or visible, and there are 10 different coins that were tossed, right? Or you could think of this as one coin tossed 10 times and then recorded, through pictures like this. Okay, so that would be 6/10 or 3/5. Now here's an interesting fact. The more you toss this coin, the more the probability of getting a heads is expected to approach 1/2. Okay, so the more trials and actual experiments there are, the closer empirical probability gets to classical probability. Now here's how we usually record the results of an empirical probability experiment. We use a frequency distribution table. So on the left, you usually record what are called the classes, and these would just be the types of results. So your classes could be winning and losing. For a coin, your classes would be heads and tails. For a die, your classes would be 1 through 6. On the right, we have all the frequencies. Right, so in this case, we have 60 wins were observed and 40 losses were observed. And then we also have a total, okay, and the total is found just by adding up all of the different frequencies. So those are the components that are needed for a frequency distribution table: the classes, the frequencies, and a total. All right, so let's try one. Example 4, computing an empirical probability. In a random sample of 500 people, 210 had type O blood, 223 had type A, 51 had type B, 16 had type AB. Set up a frequency distribution table, and then find the probability that a randomly selected person from the general population has any of these different events. All right, so we're using this phrase, a randomly selected person from the general population, meaning the results that we record and see in this experiment are supposed to reflect the general population as a whole. Okay, and that's a probability assumption that we're going to make. Okay, so let's set up the table. First, we need the classes and the frequencies. Alright, so classes would be like types of things or outcomes in this experiment. And these are blood types. So we have type O blood, type A, type B, and type AB. And then we'll also leave a spot for the total. Okay, sometimes I'll put a line there. And then the frequencies would just be the number of observed things of each class that we saw. Alright, so the frequency of type O blood would be how many people were observed with that type. Okay, so that's 210, and then 223 had type A, 51 had type B, and 16 had type AB. Now you would add all of those together to get the total, but in this case we've actually just been told the total as well. This is a sample of 500 people, so those should add up to 500. Okay, what's the probability of a random person having type O blood? Okay, well in this case, empirical probability is the observed frequency divided by the total. So this would be 210 out of 500. And we would want to put that in lowest terms. Alright, so that would be, I'll do decimals here just for something different. You can do fractions in lowest terms, but this would be 0.42. Or as a percent, this would be 42%. Okay. How about type A or type B blood? Okay, so we would add both of those in. Anybody with type A or with type B, so that would be 223 and 51. Alright, and that would be 274 people out of 500 people. And as a decimal, that would be 0.548. Okay, neither type A nor type O blood. Okay, so if it's not type A and it's not type O, then we just want to look at B and AB. So that would be 51 plus 61, or I'm sorry, 51 plus 16. All right, so that would be 67 people out of the 500. And as a decimal, that would be 0.134. Okay, and then finally a blood type other than AB. Right. Well, let's try using a difference to calculate this one. So we want to take, similar to the last section with finding probability of complements, right? We want to take the total probability, or 1, and subtract the probability or the frequency of people with type AB blood. Okay, so how many people had AB blood? 16. Right, 16 out of 500. And 16, or if you subtract 1 minus 16 out of 500, okay, that's 0.968. All right, so almost 97% of this group of people. Okay, so if you need a probability distribution table, then you would have your classes, your frequencies, the total, and then you can give 8 answers for frequencies and probabilities. Okay, so for probabilities, we would have everything as fractions in lowest terms, or decimals, or percents. Alright, and then just for fun, your textbook has a sidelight about probabilities and your fears, and they list some common probabilities for the different ways to die. Alright, so contrary to popular belief, many of the things that people fear, ways to die, are actually not that common compared to different diseases. Okay, so for example, a shark attack is 1 in 100 million, all right, versus a heart attack, which is only a 1 in 400 chance of death. All right, so you can look through that if you're interested, and that's in the textbook as well. Okay, so those are the basic concepts of probability. At this point, you should know how to calculate either a classical probability or an empirical probability, as well as make a frequency distribution table. And going on from here, we'll then apply these concepts to calculate probability questions that will need combinations and permutations as well.